So you guys are getting ready for your first exam, which is on Monday. And I just pulled up an old exam. I'm not sure how much material is on this, but I know there is a lot of material that we did cover and will be on your test this time. And so we did a lot of solving different equations and different types. And so you should be able to do that. So let's look at the first one. So solve the following equation. If you have this rational equation, first step that you want to do is you want to, if possible, factor all the denominators and then find your least common denominator. Let's see if I can write on this with no problem. Usually I don't write on this page though. I usually don't write on this PDF. I don't want to sign the document. Here we go, comment. Okay, so first thing that we want to do is we want to simplify, or we want to factor the denominators if possible. And so looking at this first one, we're looking for two numbers that multiply to give us -6 and add to give us +1. So +3 and -2 work. Actually, got you started a little bit, but it probably will be better if we use the time for a review where you guys are doing more of the problems than me doing it. And that way you guys can ask questions where you're struggling. So let me see. Okay, I just want to see how many. Okay, so you guys try those problems. Okay, so we're looking at solving different types of equations. And so the first one, 1a, is a rational equation. Let me know if you guys can't see the screen. And so the first thing we want to do is we want to factor our denominators if possible. And so we had looked at the two numbers that multiply to give our constant, -6, and add to give us our coefficient in front of x1 would be +3 and -2. And so from here, because we have an equation, we can clear our equation by multiplying both sides of the equation by our LCD of all of our fractions. And so our LCD, well, looking at this, we have x + 3 times x - 2 as a factor, or the denominator here, and just x - 2 here. So we need 1x - 2 and 1x + 3. The other thing that we need to be careful of is that we have variables in the denominator. So if any of our solutions or answers at the end gives us a value of 0 in the denominator, then it actually isn't a solution. And so we have to, and maybe it's helpful to do it at the beginning so you don't forget at the end to check. So the values that would set our denominator equal 0 are -3 and +2. So x cannot be -3 and x cannot be +2. So we're going to, like I said, again, we can clear our fractions just because it's a equation and not an expression. And so we're going to multiply by that LCD we found to be x - 2 times x plus 3. So we have to distribute it to each grouping on each side of the equation. And when we do that, the fraction pieces are going to cancel. And so when we distribute it to the first grouping, or the only piece on that left-hand side of the equal sign, your x minus 2, x plus 3's cancel. And so you're just left with that numerator, which was 5. This is equal to, well, this term 2 doesn't have a fraction, and so nothing's going to cancel. And so don't forget that you're going to be multiplying that by the x minus 2, x plus 3. Plus, so distributing this x minus 2x plus 3 to the fraction of x minus 3 over x minus 2, the x minus 2's cancel, and so you're left with the x minus 3 from the numerator of that fraction, and the piece that did not cancel, which was the x plus 3 factor. Okay, so we want to simplify this. So we want to expand. We have 5 equals. Well, if we distributed this x minus 2 times x plus 3, I know that's x squared plus x minus 6. We had factored that. And so let's distribute that 2 to that. And so that gives us 2x squared plus 2x minus 12. And then if I distribute x minus 3 times x plus 3, that's a difference of squares. So that's like the first term squared, so plus x squared, minus the last term squared, 9. So once you've distributed, let's simplify and combine like terms. So we have a 2x squared plus a 1x squared is a 3x squared. We have a 2x here. There's no other x terms there, so plus 2x. And then we have a negative 12 minus 9, that's negative 21. So we want to get all the terms to one side because we have a quadratic equation. So if we subtract 5 on both sides of our equal sign, we have 0 is equal to 3x squared plus 2x minus 26. Okay, so now we need to solve this. So we can either try to factor it, we can use the quadratic formula. I don't know what I would try to do, 72. Let's just use the quadratic formula. So x is equal to negative b, negative 2, plus or minus the square root of b squared, which is 2 squared is 4, minus 4 times a is 3 times c is negative 21, all over 2 times 3. So 4 times 3 is 12. 12 times 21 gives us 252. That's positive because 2 negatives, plus this 4 in front. So this gives us a square root of, square root of 256 all over 3. And that's equal to 16. So I have negative 2 plus or minus 16 all over 3. So we have negative 2 minus 16, that's negative 18 over 3. And we have negative 2 plus 16, which is 14 over 3.
How'd you get all over 3? Isn't it all over 6?
You're right. I don't know where I got the 3.
Oh, isn't it negative 4 times 3 times negative 26, not 21?
Okay, let's go back. You're right. I my goodness. Thanks for stopping me. So this was 4 times 3. Because that was that's a negative 26. Over 6. So 4 times 3 is 12. 12 times 26. That's 312. Positive 312. Plus this 4. That's 316. Yeah, which is not a perfect square. I don't know if 316 has any piece that's a perfect square. I know that this is even because it ends in an even number. So 2 goes in there. Let's see, 158 times. So there is a perfect square. This is even again. This goes in 79 times. And so this would be square root of 4, which is 2, root 79. All over 6. So if we factor out a 2 and cancel with the bottom, then we get negative 1 plus or minus root 79 all over 3. Yeah, that was not pretty. Oops, 79. So did any group get that? Anyone see, did I make an error somewhere? So you can see other than, oh yay. So someone did get that. That makes me feel a little more confident, especially after those couple of errors I did. Okay. Does that make sense though, how we went through it? And those were not any of the values that we had to exclude. So we should be good there. Let's see. This other one doesn't look very pretty either. It's quadratic. And so we would get everything to one side of the equation. I don't know if it's going to let me to write on it this way. Okay, so getting everything to one side of the equation and writing it in descending order. Oh, wait, that's not as bad as I thought it was. We can isolate our perfect square. So if we subtract 5 on both sides, this is negative 6y squared is equal to, So 113 minus 5, that's 108. Let's divide both sides by -6. I know that actually 6 goes into 108. $18 times. So this would be -18. We can take the square root of both sides. And so we would get y. No, it's not. Come on. Is equal to plus or minus the square root of -18. Which we can break down. So this is -1 times 9 times 2. So we could pull out our pieces. So y is equal to plus or minus. Well, square root of 9 is 3. Square root of -1 is I root 2. So what about that one? You guys do okay? Yay. For some reason, I was thinking that was a trinomial that I was going to have to try to factor that. I didn't see that they were both constants in there. Excuse me. So it looked really ugly at first, but once I noticed that there wasn't a term with y, that wasn't bad whatsoever. Okay, so next type we have is a radical equation. So first step you want to do is isolate your radical. And so we can do that by subtracting 2 on both sides. So we have the square root of x plus 4 is equal to, so let's subtract 2 on both sides, -x minus 2. So once you've isolated a radical, there's only one in this expression, but once you've isolated it, you want to raise both sides to the power or index to clear the radical. And so in this case, we would square both sides. And so we have x plus 4 is equal to, and we need to distribute -x minus 2 times -x minus 2. So we have x plus 4 is equal to, so distributing it, this is x squared plus 2x plus 2x plus 4. So I have x plus 4 is equal to x squared plus 4x plus 4. So again, quadratic, got to get everything to one side of my equation. So we can subtract x and subtract 4. So we get 0 is equal to x squared plus 3x. Constants cancel. So solve by factoring. We can pull out an x. 0 is equal to x times x plus 3, and then set each factor equal to 0. So we're looking at when is x equal to 0, and when is x plus 3 equal to 0. So we need to be careful because we can get extraneous solutions. So because we squared both sides of our equation, if you raise it to an even power, we have to check. And so if we plug back 0 in wherever we see an x here, well, this is square root of 0 plus 4. So square root of 4, that would give me a 2 here. Is 2 plus 2, is that equal to negative, plugging in a 0? Well, 4 doesn't equal negative 0, so x can't be 0. And so now let's plug in negative 3 and see if that works. So negative 3 plus 4 underneath the radical is 1. Square root of 1 is 1. Plus 2. Does this equal negative? Now plug in negative 3 where we see the x. So 1 plus 2 is 3. 3 is equal to 3. And so this is a part of our solution. Okay, so now let's let you guys try. If I can pull it. Sorry, it's frozen. Okay. I'm noticing that we did not do nonlinear inequalities like this has here. We did it with graphing yesterday, so you wouldn't have to worry about that. And we haven't yet covered non-linear, again, inequalities or rational inequalities. So that actually would not be on your test. But number 2 would be something that we have covered. And so you should be able to do that one. So write that one down real quick, and then I'll have you guys try it. Okay, so you guys had a chance to work on it, and we saw that so most of you said that your answer was 5/4. Got one that was 3. So let's walk through this. So absolute value equations, they're different than the inequalities, but absolute value equations, you want to isolate first the absolute value. And so we do not want that 3/4 in front of this absolute value. So there's a couple ways that we can think about doing this. You can clear your fraction by multiplying both sides by 4, but we're going to have to get rid of that 3 also. So let's think of it as multiplying by the reciprocal. So reciprocal of 3/4 is 4/3, and that multiplying would make this a 1 in front of the absolute value which we want. But if we do something to one side, we got to do it to the other side. So let's multiply the other side by 4/3. And so we're left on the left-hand side with the absolute value. Oops. Of 8t minus 12 is equal to, well, the nice thing here is that 3 goes into 6 evenly twice. And so we're left with that 4 times 2, which is 8, all times t minus 1. So in order, maybe let's just distribute that negative, or 8 as we're there. So this is the absolute value of 8t minus 12 is equal to 8t minus 8. So the absolute value is isolated. In order to drop the absolute value, we want to rewrite this as 2 separate equations. So what is inside the absolute value, 8t minus 12, equal to the other side, which is 8t minus 12, I'm sorry, minus 8. Or it could be what was inside the absolute value, 8t minus 12, that could equal the negative of the whole other side. So put parentheses around the whole thing. And so we want to solve each equation separately. And so if we, and the first equation's linear, if we try to get the 8t to the other side, notice those cancel, and you're left with just -12 equals -8. Well, that's false. And so this means there's no solution for that piece. So we want to do the same thing. We want to solve for t in the other equation. And so we have 8t minus 12 is equal to, so distribute our negative, we have -8t plus 8. Get all the terms with t on one side, so let's add 8t to both sides. And let's add 12 to both sides. So we have 16t is equal to 8 plus 12 is 20. Divide through by 16 on both sides of our equation, we get t is equal to, those are both divisible by 4. 4 goes into 25 times and 4 goes into 16 4 times. So there's the 5/4. So if you didn't get 5/4, then hopefully you see where you were struggling or where you went wrong, or if you got caught up. Hopefully you saw how to proceed past that point. Okay, so I'm just giving you a couple more problems to try out. So we have a compound inequality, 2 plus x is less than 3x minus 2 is less than or equal to 5x plus 2. And so this one was a challenging problem from your book, but in a different semester, we would go over these. So make sure the key on this one is you have to break it up as two separate inequalities. So take the middle and the piece before it, and take the middle and the piece after it. It's an and statement, so it has to be what they have in common. So let you try that. And then you also have a compound absolute value inequality. So you have to rewrite that too as two separate inequalities, and this is an and statement again. So I want you to try those. So I'll give you a couple minutes to do that. Okay, so we have a compound inequality, and we want to break this up because we have x's on each side of that compound inequality. So we want to break this up as 2 plus x is less than 3x minus 2, and which is a intersection, meaning intersection. We're looking at when is 3x minus 2 less than or equal to 5x plus 2. So we want to solve each inequality separately. And because this is an and statement, we're looking at when they have the same solution area in common. So this is a nonlinear inequality. Get variables to one side, constants on the other. So we could subtract 3x on both sides. Let's subtract 2 on both sides. So we get x minus 3x is negative 2x is less than negative 4. If we divide by a negative number, which I'm going to do, we have to flip our inequality sign because I want x by itself. And so this is now a greater than sign. Oops. So x is greater than negative 2 divided by, sorry, negative 4 divided by negative 2 is positive 2. Okay, so here we have x is greater than 2. So it's everything bigger than 2, so everything is shaded to the right. So solve the other inequality if we get all the x's to one side, all the constants to the other side. So let's subtract maybe 5x on both sides. Add 2 to both sides. So we have 3x minus 5x is negative 2x, is less than or equal to positive 4. Divide again by a negative, you're going to flip the inequality sign. So this is now greater than or equal to, x is greater than or equal to negative 2. And so this would be everything from negative 2 to infinity, and we include, so there's a bracket. So what they share in common, where they overlap, is starting at 2 but not including to infinity. Okay, so our solution is 2 to infinity. So any number that you choose that is bigger than 2 should satisfy that compound inequality. So absolute value inequality, well, depending on where side the inequality is, depends on how you're going to drop the absolute value and how you're going to rewrite it. Since this is a compound absolute value, we can do something similar like we did up above. So we can break this up into 2 separate inequalities. So this is the same thing as the absolute value of x minus 2 all over 2 has the greater than or equal to 4. We also have the absolute value, so that's the whole absolute value of the fraction. We have the absolute value, and this is an and statement again. The absolute value of x minus 2 all over 2 has to be less than 10. I was hoping I could add space in here. Try that one more time. Okay, I can't add space. Okay, so to drop that absolute value, if it's a greater than or equals to sign, you break it down as 2 separate inequalities. We're looking at when is this absolute value, x, what was inside x minus 2 all over 2 less than or equal to 4, negative 4, sorry. Or we're looking at when is what's inside the absolute value, x minus 2 all over 2 greater than or equal to 4. Then we have this and statement again. So if it's a less than sign for an absolute value, then you sandwich it in between the negative and the positive. So this would be negative 10 is less than x minus 2 all over 2, which is less than 10. So let's cross this out for now. So let's solve each piece. So solving this one, this first inequality, we can get rid of the fraction by multiplying everything through by 2. So 2 here. Oops. So that cancels. We're left with x minus 2 is less than or equal to negative 8. Add 2 to both sides, we get x is less than or equal to negative 6. Or, so solving this piece, same idea, we can get rid of the fraction by multiplying both sides of the inequality by 2. That cancels, we're left with x minus 2 is greater than or equal to 8. Add 2 to both sides, x is greater than or equal to 10. Okay. And then the other side, that compound inequality, we can clear the fraction by multiplying all 3 sides of the inequality by 2. So we get negative 20 is less than x minus 2 is less than 20. So if we add 2 to both sides, we get negative 18 is less than x is less than 22. Okay, so let's graph it. I'm just, let's say that this is 22. Let's say that this is where 10 is. I'm just going to put in values negative 6, negative 18. And for x is less than or equal to negative 6, so that is a bracket and everything shaded to the left. Or means plus x is greater than or equal to 10, so that's a bracket, everything shaded to the right. And then if I graphed the compound inequality piece, so it was everything that was between negative 18 and 22. So I have a parentheses on negative 18, I have a parentheses on 22, and I have everything shaded in between. So we need to take what they share in common, and that is our solution. Okay, so where are they overlapping? They're overlapping, or they're starting to overlap at negative 18, but not including negative 18. Negative 6 is included here and here, so we're going to have a bracket there. And they're overlapping here at positive 10 to 22. So our solution is parentheses negative 18 to negative 6 bracket, union bracket 10 to 22, parentheses. Okay, so the domain, let's look at that real quick, because that's similar to what we're doing here. And the fact that when we find it, it's what they have in common. So we have f of x is given to be the square root of 2x minus 6 all over x squared minus x minus 12. And it wants us to find the domain of f of x. Okay, so for domain, remember we go and we look for trouble spots. So domain are all values of x that you can plug into your equation and you would get back a real number. So trouble spots are values if you plug it in for x, that function is undefined, meaning it gives you a 0 in the denominator, or if it gives you a negative number underneath an even power radical. That's an imaginary number, complex number, and so that would not be part of our domain. And so there's two pieces in here we have to worry about. We can't have what's underneath the radical. That can't be negative. Excuse me. So we need 2x minus 6 has to be bigger than or equal to 0. I'm okay to have the square root of 0 as long as it's in the numerator and not denominator. The other piece is the denominator, we're okay for any value for x that we plug in there except for the value of x that sets that equal to 0. So we have to exclude the value where x squared minus x minus 12. This cannot equal 0. This is an and statement. So both of these things have to hold true in order for it to be part of the domain of f of x. So solve each piece. So solving this piece, add 6 to both sides, we get 2x is greater than or equal to 6. Divide by 2, we get x is greater than or equal to 3. So in order to be in the domain of f of x, that number has to be bigger than or equal to 3. And then let's make sure let's find out when this is 0. So factor it. So I'm looking at -4 plus 3. So x minus 4, x plus 3. This can't be 0. So x cannot be 4, and x cannot be -3. Well, x cannot be -3. We know that x has to be bigger than or equal to 3. So this isn't even in this set. It doesn't even fall there. So since it's not contained in there, we don't have to worry about it. But 4 is greater than 3. And so we have to look at excluding that 4. So we're coming from 3. We're going to go all the way to 4, but we can't include 4, so we're going to put a parentheses. Union, we can go from 4 to infinity, but not include 4. Or that's a solution, or that's our domain actually. Okay, so I apologize. There was a huge chunk that I thought I was recording and I forgot to push record. We just came back from break and we're looking at some more problems for reviewing for the exam on Monday. And this was from a review from test 2. I'm not sure if I posted this, but this half of the material on this test for test 2 is covered on your first exam. Okay, so for this first one, it says f of x is equal to 1 over x plus 2, that quantity, minus 3. Answer the following. So what is the parent function? And then it wanted us to graph what that parent function looks like. So you should all know what that parent function is. So it's the reciprocal function, 1 over x. Graphing that, you had in the third quadrant the shape. You have vertical and horizontal asymptotes, and in the first quadrant it looked like this. Never crosses the x or the y axis. And then what are the horizontal and vertical asymptotes of this parent function? So that is something we haven't talked about. I just told you that, but that's something that we're going to look at in the next chapter, graphing rational functions, and 1 over x is a rational function. You can't have a value of x in the denominator, it's undefined. So we have a vertical asymptote there in this graph. As x is going to infinity or negative infinity, it's getting closer and closer to the x-axis. It's getting closer and closer to the value of 0, but it is never equal to 0. So what is the domain and the range? The domain of the parent function. So the domain are all values that we can plug in for x and get back a real number. So the only trouble spot that we have for this equation is when x is equal to 0. So the domain is going to be all real numbers except 0, or we could state that as negative infinity to 0 with a parentheses, union, parentheses 0 to infinity. The range is pretty much the same thing. You're hitting all the y values on your graph from negative infinity all the way up until you get to 0. There's no value of y that is 0. And then everything above 0 to infinity. So our range is also negative infinity to infinity. I'm sorry, negative infinity to 0, parentheses union 0 to infinity. Find the x and the y intercepts of the parent function. If they exist, there's none. So what transformations are you performing on the parent function to get the graph of f of x? So we're looking at what transformations we're doing. And so notice the +2 here. In order to get that, you would have plugged in that whole expression, x plus 2, wherever you saw an x right here. And so that is affecting it horizontally. And it's opposite horizontally. So this +2, we're going to go to the left 2 units. And then the -3 outside. In order to get that, we would have had to subtract 3 out here. So we subtract it from f of x. And so that affects it vertically. And so we're going to, and it's a minus, so we're going to go down 3 units. Actually knowing where these asymptotes are can be kind of helpful because those are how they're going to shift. Those asymptotes are going to shift to the left 2 units for the vertical one, and it's going to shift down 3 units for our horizontal one. And so we'll pretty much get the same picture, but like that. So let me redraw this. And it's a graph f of x. So let's have our x-axis, our y-axis. We have left 2 units. So left 2 units, that's going to affect our vertical asymptote. So instead of being on the y-axis, we're now going to be -2. We'll usually see dotted lines like that denoting there's an asymptote, but technically they're really not on the graph. It's just helping us graph it. And then we're going to shift this down 3 units. And we're shifting, let's shift our vertical asymptote down 3 units. So the x-axis where it was before is now vertical asymptote at -3. And so this piece down here on our parent function is now shifted, and it's now down in here. So this upper piece that was in the first quadrant of our parent function is shifting so that our vertical asymptote, same shape, is like this. So what is the horizontal and the vertical asymptote? Well, the horizontal, that is the line y equals -3. And the vertical lines are in the form x equals, this is x equals -2. Domain and range. Our domain and range have changed. Our domain, we no longer are going to include 2. Can't have, or -2. We can't have 0 in the denominator. So our domain for f of x is all numbers from -infinity to -2, but not including, so parentheses, union, everything from -2 to infinity. The range, though those are all the y values you're hitting on the graph, it's all the range. And we're not including -3. And so we're coming from -infinity all the way to -3, parentheses, union, -3 to infinity. And then find any x or y intercepts if they exist on f of x. So x-intercepts, again, is when y is equal to 0. So I'm going to set my f of x is y equal to 0. So we have 0 is equal to 1 over x plus 2 minus 3. So I notice I could add 3 to both sides. So doing that, we get 3 is equal to that fraction 1 over x plus 2. I can clear my fraction by multiplying x plus 2 on both sides of my equal sign. So doing that, we get 3 times x times the quantity x plus 2. So 3 times x is 3x. Plus 3 times 2 is 6 equals 1. Subtract 6, divide by 3. So we get 3x equals negative 5. X is equal to negative 5/3. So that's about negative 2 and, well, that's negative 1 2/3. So my graph's a little off when oh no, that looks good. That looks good. It's x. And then y. Y is actually easier. We're going to let x equal to 0. So if we look at f of 0, this is 1 over 0 plus 2 in the denominator, or 2, minus 3. I need a common denominator, so I'm going to just write minus 3 is negative 6/2. And this is equal to negative 5/2, which is equal to negative 2.5. Wait, negative 2, yeah, negative 2.5. So in between right here. Okay, so we found the x-intercept and we found the y-intercept. Okay, so you should be able to answer questions about graphs and transformations. Recall we did variation problems. So that's like the next example. So it says the number of stairs in a stairwell of a tall building and other structures vary directly as the height of the structure. The base of the pedestal for the Statue of Liberty is 47 meters tall with 192 stairs from the ground level to the observation dock at the top of the pedestal at the statue's feet. So A, find a constant of variation and write the variation equation. Okay, so we want to go back and we want to pick this out. It says the number of stairs in a stairwell of a tall building and other structures varies directly with the height of the structure. Okay, so the number of stairs maybe let's call this S. So S, number of stairs, varies directly. This is where we had our constant K in here. Directly as the height of the structure. So maybe we can put H in here for height. Or building. Okay, so now it gives us enough information that we can figure out what K is. So it says that the Statue of Liberty is 47 meters tall with 192 stairs. So we know the number of stairs is 192. So we know 192 is equal to our constant K times the height of the building. And the height of our building we're given was 47 meters. So we can find K by dividing both sides by 192. I'm sorry, dividing both sides by 47. So 192 divided by 47. And it doesn't go in evenly. So S is equal to, I'm going to keep it as a fraction. Or not S, K is equal to 192 over 47. So now we have the equation that we could help solve any question they ask of this now. Can't be. Okay, so we have S is equal to 192 over 47 times H. Okay, so find the constant of the variation and write the variation equation, that's B. Graph the variation equation. I'm not going to graph it, but basically this is a linear line. Use the graph to estimate the number of stairs. I'm not going to do that, but let's do this. Estimate the number of stairs from the ground level to the observation desk of the Statue of Liberty's crown. That's 81 meters above the ground level. The base of the base. And then we want to okay, so basically, I was wondering if we had to subtract anything, but it looks like that we want to find out how many stairs there are when it's 81 meters. And so we're going to look at this as our height here, and we can plug it into this equation. And so for part D, now this was C. So we're not doing all these parts. I'm looking at S is equal to 192 all over 47 times 81. So that is approximately 331. Okay, so I didn't graph it. We could technically graph this. And we could put it on one of the graphing utilities and we could guess. But we're not really looking at that for now. So let's just move on. So we looked at piecewise functions. So piecewise functions, those were where you were graphing bits and pieces. There's different equations depending on which values you're using for x. So if you're plugging in a number less than -3, you would be using this first equation. If you were using any number that was between -3 including and 2 not including, you're going to use the second equation. And then any number that is bigger, you're going to use this, then 2, or including. So you want to graph each piece separately. Well, I graph them together, but kind of separately at the same same time. So we have x here. We have y equals negative x minus 3. When we plug in numbers, we always want to test the values of our inequality, even if it's not included. So negative 3 is the endpoint of our inequality, but it's not included. We still want to see what's happening there because we can get really close. So negative of negative 3 minus 3. Negative of negative 3 is 3, minus 3 equals 0. I put a little note to myself. This is an open circle here. Because it was strictly less than. So any number less than negative 3. So for instance, negative 4, minus 4. So that's a positive 4 minus 3 is 1. Okay. We know this is a graph of a linear line. So it's a linear equation, it's just a line. So at negative 3, 0, we have an open circle. At negative 4, 1, we have a closed circle. And this is a line. So it's going to extend to the left because those are for all values of x less than negative 3. And so now graph the piece for 9 minus x squared. Well, I can tell that this is a parabola. It's a parabola that's facing downwards because of the negative here. And it shifted up 9 units. We can think of it as this way. This is actually in standard form, negative x squared plus 9. So if I kind of use my reasoning there, I know I have a vertex at 0, 9. Or just plug it in 0 for x, you get 9 back for y. I need to see what's happening at my endpoints, even if they're not included. Negative 3 in my inequality. If I plug it in here, negative 3 quantity squared is 9 with a negative in front. So that's negative 9 plus 9 is 0. So when x is negative 3, I get 0. And this has the equal to part, so it's included. So put a circle, closed circle. So notice that's where an open circle is from the other piece. But because of the second equation, now I can close it. I know it's a parabola shape. And then I need to see what's happening at 2, even though it's not included, but it's the end value of my inequality. So plugging in 2 for x, I get 9 minus 2 squared. 9 minus 4 is 5. So when x is 2, y is 5. And it's an open circle. So I have one more piece that I need to graph, and that is f of x equals 4. And that's for everything bigger than or equal to 2. So at 2, I get 4. At 3, I get 4. At 5, I get 4. Any number I plug in, I get 4. 2 is an inbound, so this is, we're going to have a closed circle here. So at 2, I have a positive 4, so it's a closed circle right below that open circle. And it's a horizontal line. looking like this. So putting all the pieces together, we graphed it. Now we should be able to answer all the different questions: domain, range, increasing, decreasing, anything else that is thrown at you. So domain, basically we're given the domain. It's the union of all of these inequalities. So it's all these x values plus all these x values plus all these x values. So we're looking at everything from negative infinity to -3, not including, but then we're including -3 here to 2, not including 2, but we'd include 2 here and everything bigger. So our domain is actually all real numbers. Our range, I wouldn't know that range without graphing this. I'm looking at my y values that I'm hitting on the graph. Notice that the smallest y value on this graph is 0. And then I'm hitting all the y values up. But this line, this linear equation, this line here is going to extend to positive infinity as x goes to negative infinity. So I'm hitting all my y values starting at 0, including to positive infinity. So increasing, decreasing, and constant. So when we're looking at increasing, decreasing, and constant, we're looking at the values, the places where the graph is going down. Sorry. So we're looking at, I'm trying to do too many things at once. When it's increasing, decreasing, and constant, we're trying to find the values of x where that is occurring. Okay, so if I'm looking at increasing, I'm looking at from left to right and going up. So from left to right, I'm going up, it looks like starting here at -3. This graph goes upwards, and then it stops at x equals 0. So my x values in here are starting from -3 going to 0. There's no other place in this picture that I am going to walk uphill going from left to right. So now looking at my decreasing, so going down from left to right, well, that would be this piece until I get to -3. So I'm hitting everything to the left. So negative infinity to -3, bracket, union, and then we're going down on this little segment. And so that values of x are 0, and I'm stopping at 2. Not including, because it's an open circle there. So I'm going to do bracket 0, comma 2 parentheses. And then the last piece where it's constant, that's where it's a horizontal line. So all the x values where it's a horizontal line, well, that looks like it's starting at 2, and then it's going on forever to the right to infinity. So it's constant from x equals 2 to infinity. So it's asking us, when is f of x greater than 0? Well, it looks like it's greater than 0 except for one value. This value right here at 3, -3, we have it equal to 0. So f of x is greater than 0 for all values except x equals -3, or I can say that from negative infinity to -3. parentheses, union -3 to infinity. Whereas f of x strictly less than 0, well, this graph never crosses the x-axis. I mean, it never, well, it never crosses. It does touch. There's no y values that are negative, and so nowhere. Or maybe I might put the empty set. Doesn't happen. Okay, so kind of looking at a couple of symmetry problems. So if you're given a graph, you should be able to graph the rest of it given information. So in this example, you're given a graph and it's telling you that the function is even, and it's telling you to complete the rest of the graph. So what it means to be even, recall, is if you can plug in the negative value in for x, you get back the same value as if you had plugged in the positive value of x. Okay, so that's basically saying that if I have some point xy on the graph, then I also know that negative x, same y value, y, is also a point on the graph. And so from here, I can just choose points from my graph and get other points that have to be on there. So let me count. So it looks like it's crossing the x-axis at -5, 0. And so I notice I have a point at -5, 0. And so by my rule, then +5, 0 is also a point on my graph. Maybe hit another important point. So maybe this piece down here, which is the minimum, a local minimum. So let's figure out what x value, so that's 1, 2, 3. So that's at -3 for x, and it is 1, 2, 3, 4. -4 for y. X value is going to change. It's going to be now positive. Y value, though, is staying the same of -4. We now have a point at 3, -4 is also a point on the graph. And so I notice that it's also, even functions are special. They're symmetrical with the y-axis. So if I folded my paper along this y-axis, I know it's going to be a mirror image. So just finding a couple of those important points, we get the rest of the graph. Okay, so determine whether the function is even using x equals k. So we didn't usually use a different variable. We used the negative x, but it doesn't matter. So basically what that's saying I'm going to actually write it down here if that's okay. We have f of x is equal to 4 times the absolute value of x plus 10x plus 8. Determine whether it's even. Is f of x even? Show using x equals k. So basically, even again, if we plug in positive k, and wherever we see an x, we better get back the same thing as if we plugged in negative k wherever we see an x. So if we go into this equation and we plug in positive k wherever we see an x, so let's go and do that. So we have 4, you have an absolute value, you're going to plug in x there, I'm sorry, k, plus 10, you see an x, I'm going to put parentheses, plus 8. Now I'm going to have to do this twice, one with positive k and one with negative k. Okay, so now if I plug in negative k, wherever I see an x, well, we're assuming k is bigger than 0. We could have assumed it was less than 0. It's going to work either way because we're flopping it. But assuming that it's bigger than 0, if I take the absolute value of a number that's bigger than 0, I'm going to get the same number, right? Or the same thing as dropping the absolute value. So I can say this is the same thing then as 4 times k plus 10k plus 8. So that's f of k. Now let's look at f of negative k. So this is equal to 4. Well, the absolute value of negative k, we know that k is positive, so this is an absolute value of a negative number, is going to give us back the positive. It's going to be positive k. Minus 10 times k, so minus 10k plus 8. So this is f of negative k. Oops. Oh, I can go back. Looking at this, are they the exact same thing? And they're almost the exact same thing, except for one has plus and one has a minus. So these do not equal each other, and so it's not an even function. So same sort of idea, you could test that 12 was the same, similar. So let me just kind of jump to 13. So looking at this, you're given that you have an odd function. So recall what it means to be odd. That means if you plug in a negative value for your x value, it's going to change the sign on your y value. It's going to give you back negative f of x. So what that's saying is if you have some point xy on your graph of f of x, and it's an it's an odd function, then plugging in negative x will give you back the point y value of negative y. Other thing about odd functions are they're symmetrical across the origin. So I folded this paper in force. It should be a mirror image. And so I know that's going to look like this shape, but let's find some important points. So x-intercept is good. So 1, 2, 3, 4. So that's a negative 5. And so I have a point at negative 5, 0. Change both x and y. I would get now a point at 5, 0. I have a maximum value here at negative 3, 3. So my point negative 3, 3 changing signs for both of those are now 3, -3. And so the rest of the picture would look like that, being an odd function. Oops. So, was that what you were thinking of when you said symmetry? I'm hoping.